So you can see in the Ethernet header there is a field called type field, right? Here the value of the type field specified is 806, and 806 is identifier of the ARP protocol. So 806 is the standard value which identifies that the protocol is ARP protocol. Since the Ethernet header's type field contains 806, it means that the next protocol which is running above the data link layer in the TCP/IP stack is the ARP protocol, right? So after the type field, the Ethernet header carries the payload. Now because the value of the type field is 806, it means that this payload contains ARP related information. Now as we know that ARP protocol comprises of two types of messages, the ARP broadcast request message and the ARP reply message. So in this info part, the ARP message could be ARP request message or ARP reply message. The value 806 only says that the payload contains ARP message. It do not say whether that message is ARP request message or ARP reply message. So to know whether the type of ARP message is ARP request message or ARP reply message, in this payload we inspect the first byte. So if the value of the first byte is 1, it means the payload represents the ARP request message, and if this value is 2, it means that the payload represents the ARP reply message. So in this case, the first byte is 1. It means that this is ARP broadcast request message. So the payload represents ARP broadcast request message. Now if you see the contents of the ARP broadcast request message, it has the source MAC address, that is the MAC address of the machine which generated ARP broadcast message. So in this case, the source MAC address is ME, that is this value, and the IP address of the source machine, that is 12.1.1.3. So it is the IP address of the interface out of which ARP broadcast message was launched by the source machine. So you can see that the ARP broadcast request message was emitted out of interface IFE, which has the IP address 12.1.1.3. Therefore source IP address will be 12.1.1.3 and the source MAC address will be the MAC address of that particular interface, right? And the destination MAC address in the ARP broadcast message is a question mark, because this is the value which the machine E is trying to find out. And the destination IP address is 12.1.1.2, that is this value for which the machine E is trying to find the MAC address, right? So these are the contents of ARP broadcast request message. Also, I would like to clarify one more thing. When the machine E decides to launch ARP broadcast message, how machine E decides whether it has to launch the ARP broadcast request message out of interface IFE or out of interface IFE1, right? So for that, machine E checks that for which IP address it is trying to resolve the ARP. So in this case, it is trying to resolve the ARP for IP address 12.1.1.2. Now machine E will check that which local interface is configured with the IP address such that this IP address falls in the subnet of that particular interface. So in this example, machine E has interface IFE which is configured with the IP address 12.1.1.3/24. So clearly this IP address for which ARP is being resolved falls in the subnet 12.1.1.0/24. which is configured on interface IFE, and therefore machine E launches the ARP broadcast request out of interface IFE and not IFE1. So this is one important concept here, that how the machine decides out of which interface it has to launch the ARP broadcast request message. So going forward, how E would know D's MAC address? So let us resume with the steps where we left. So in step 7, ARP request packet is received by all the interface connected to the wire. So machine E launched ARP broadcast request message, and this ARP broadcast request message will be received by all the machines which are connected to the wire. Right? So the data link layer of none of the machine which receives this ARP request packet discards the ARP request packet because destination MAC address is equal to the broadcast address. So when this condition happens, then data link layer of none of the receiving machines discards the packet. That is, data link layer accepts the packet. So all receiving machines now chops off the Ethernet header and hand over the next header in the packet, which is the ARP header, to the ARP protocol. So data link layer hands over the frame to the next layer in the TCP IP stack, which is the ARP protocol. ARP protocol running on top of data link layer sees the destination IP address in the ARP packet. Now, ARP protocol checks that if destination IP address is equal to the IP address of the receiving interface machine, that is the receiving machine sends back ARP reply, else discards the packet. So in this example, the condition that is specified in step 11 is true only for machine D. The ARP protocol for the router as well as for the machine F discards the packet because destination IP address that is specified in the ARP request message header is not equal to IP address of the receiving interface. So the condition of the step 11 is true only in case of machine D. So it is the machine D which replies back with the ARP reply. So what are the contents of the ARP reply message? The ARP reply will have the source MAC address, which is MD. So for the ARP reply message, D is the source machine. So source MAC address will be MD and destination MAC address will be ME. Source IP address will be 12.1.1.2. That is this IP address, because ARP reply will be sent back from the same interface from which ARP broadcast request message was received. And the destination IP address will be 12.1.1.3. And the type of the message will be ARP reply. So ARP reply is placed on the wire by the machine D and is received by all the interfaces connected to the wire again. Right? So if you say, let us discuss the ARP reply, if the machine D launches the ARP reply message, it will again be received by all the interfaces which are connected to the wire. So all the machines receives the packet because they are connected to the same wire. It doesn't matter what is the type of packet. So all receiving machines discards the packet because destination MAC address in the Ethernet header of the packet is not equal to the receiving interface MAC address. Right? So remember here, all receiving machines means the machines which are connected to the wire except the machine E. ARP reply message is processed by E only because the destination MAC address in the Ethernet header is equal to ME. So when the machine E processes the ARP reply message, it will fill its ARP table with the information. This information is actually wrong. It will fill its ARP table with the IP address 12.1.1.2 and the MAC address is MD and the outgoing interface is IFE. So machine E will fill its ARP cache with this information. So machine E will note that to reach a neighbor 12.1.1.2, the MAC address of the neighbor is MD and the outgoing interface is IEF. Sorry, outgoing interface is IFE. Right? So remember, all the machines which are connected to the same wire are actually neighbors of each other. They are considered as neighbors of each other because they are connected to each other directly by the same wire. And ARP table entry contains the IP address to MAC address mapping of neighbor interfaces. So this is how ARP is resolved by the machine E for neighbor D. So going forward, this slide shows the contents of the ARP reply message. Here, because the first byte value is 2, it means that the payload part in the Ethernet header is actually the ARP reply message. And in this ARP reply message, you have the source MAC address field, which is the MAC address of the machine D, and the source IP address field, which is 12.1.1.2, right? And the destination MAC address will be ME, that is E, because machine D is replying back to machine E. Therefore, the destination MAC address will be the MAC address of machine E, and destination IP address will be the IP address of the machine E, right? So here the replier becomes the source and the machine which actually generated the ARP broadcast message becomes the destination. So one thing to note here is that in the Ethernet header, in the ARP reply message, the source MAC field is the MAC address of the ARP replier, which is machine D, and the destination MAC address is the MAC address of the machine E, which was the generator of ARP broadcast message. That is ARP MAC address of the machine E. So that is the reason, because we have a destination MAC address as a MAC address of some specific machine. Therefore, ARP reply messages are unicast messages on data link layer, right? Unicast means they are directed towards a particular machine which is connected to the wire. So going forward, so in step 6, when E receives the ARP reply message, the machine E will update its ARP table with the following entry. So it will update its ARP table with the IP address 12.1.1.2, which is the IP address of the neighbor, with the MAC address of the neighbor, and the outgoing interface will be IFE, right? So remember that the ARP table is always updated using source MAC and source IP address fields in the ARP reply message. Not ARP request message, only ARP reply message. So in the previous slide, you can see that the source MAC and the source IP addresses which are specified in the ARP reply message are these fields, and using these fields, when the machine E receives ARP reply message, the machine E uses these fields to populate its ARP table, right? So E now knows that what it was looking for, that is D's MAC address. So E now inserts D's MAC address in the Ethernet header it was preparing before and place it on the wire when the machine E is ready after cooking up the packet. So that particular packet, when placed on the wire, is received by all the interfaces connected to the wire. All discards the packet, but machine D accepts the packet. And we have already discussed that this is called thrashing. So the packet which is placed by the machine E after resolving the ARP is the packet which contains source MAC address as the MAC address of the machine E and the destination MAC address as the MAC address of the machine D. So data from E has been successfully transmitted to D, right? So when machine E wants to send a data to the machine D, machine E has to resolve the ARP first. Only after resolving the ARP, actual data communication between the machine E and machine D will happen. So points to note here are these. Inquiring machine. Inquiring machine means the machine which wants to know the MAC address for a certain IP address. That is the machine which is launching the ARP broadcast request message. So inquiring machine populates its ARP table using ARP reply message only, right? ARP request message is a broadcast message. Why? Because the destination MAC address in the Ethernet header is the broadcast address, whereas ARP reply message is a unicast message. Why? Because the destination MAC address in the Ethernet header of ARP reply message is actually the MAC address of the broadcast request generator. So ARP messages never crosses L3 router boundary and confined within a subnet. So that we have already discussed, that whatever be the type of message, whether it is a ARP broadcast message or ARP reply message, it will never cross the L3 router boundary. That is, that message has nothing to do on this side of the router. And ARP works on the layer 2 only. And number of ARP entries is equal to the number of devices connected to the wire, right? So in this case, machine E, if machine E wants to carry out communication with the machine D or machine F or the router itself, then the machine E will have to resolve the ARP for machine D, for machine F, as well as for the router also. So for this topology, the number of ARP entries which each machine is expected to have is 3, because every machine which is connected to this wire has 3 neighbors. So finally, you are advised to read more about the ARP online. You can just Google it and you can read more about the ARP protocol. And you should have at least one glance at the exact message formats. We have given a clear idea of how ARP works. So remembering exact message format is not required as long as you can explain the protocol functioning and main fields in the message, right? So don't try to mug up the message formats. Only the main fields which are required to explain the functioning of the protocol, it's more than enough that you remember only those fields, right? So it is not true only for ARP header, but for any protocol. For example, IP header has so many fields, but most of the time you need to remember only 3 or 4 fields in order to explain the functionality of the IP protocol.